Hi Joyce, currently everyone is working on the circle problems that you see from homework. They should still be up on the board, but just in case they get erased, I'm going to take pictures so you can see them, okay? With any questions on 17, 27, 41, 45, 50. So they went up to the boards and worked them out. And now my computer is frozen. You know what that's like. So hold on. If you need to check number 50, you can go ahead and pause it right now. There's number 50. And then if you need to check number 14, if you haven't yet already. I have him. Hold on, he's coming. Here he is. You can check number 14. Otherwise, you know where the solution key is, and you can check the rest. So let me get rid of that. Let me see if I can get rid of that. Okay. And then here we go. As soon as they finish, they're on their last problem with Amanda Devisarian.
Oh, you're subtracting this over? Yes.
Linearization, sensitivity, and differentials. I'll just start talking and I'll come back. Yes. That's something. Possibly. What
do you want to talk about?
I'm waiting. You got it? Yes. Sweet. Linearization, sensitivity, and differentials.
Oh, I remember sensitivity.
Sensitivity we're not going to stress tons about just because it's not on the AP, but it is a kind of cool application. So I might put, I'll be making your guys' homework assignment next period. I might put like 1 or 2 just because they're interesting. I think they're interesting. But we're not going to stress too much. Someone from last year. What is linearization? Uh-oh. It's okay, they're catching up, Joyce. They just sat down. What is linearization? What do we have up here? What is this? L of x. Linearization equals f of a, y values, plus f prime of a, a slope times x minus a. This looks an awful lot like what's the most important line that we know?
Tangent line. So it's
what's the tangent line?
Y minus y1.
Y minus y1, which could be f of a, equals m, which is f prime of a. The derivative is the slope of the tangent times x minus
Approximation, right? So
local linear approximation, otherwise known as linearization.
oh, it's the same thing? Like the synonyms?
Synonyms?
Synonym. Will you say as nothing to the table?
That's Jacob Gigante.
Who's Jacob Gigante? He's
Grace
like the best
Gigante's
runner
older
there.
brother who, yes, became president. He goes to Wheaton College back in Chicago. So, is this formula really supposed to be super complicated?
No.
Nope, it's just a tangent line. Is a tangent line applied? Is a tangent line applied how? Well, first of all, before we say how it's applied, technically this formula is a standard linear approximation. You guys are going to see there are actually other ways of approximating besides lines, which makes sense because linear approximations are only good, only fairly good, only kind of good for linear approximations are only good for, well, but at the instant it's not an approximation, you're just finding the derivative of that. But we can use a tangent line to approximate for
another.
put quotes. Good approximation because good is obviously relative. The good approximation for x values. Look at this. If you zoom in on any graph, eventually it's going to look like on most graphs, besides maybe sine of 1 over x or something. So if you zoom in on any normal continuous graph, what's what's a sliver of it always going to end up looking like? A line. So if you zoom in around what? Around A, which is why A is called the center of the approximation. Another way of saying it possibly is that it's approximated around. It's approximated around x equals A. The center of the approximation is x equals A. So this is a fairly good approximation for x values close. Once again, let's put close in quotation marks. Close to A. It can be a fairly good approximation for values close to A.
We can find exact value, let me find a approximate.
We can't always find the exact value.
Not all functions are easy to find exact, and you'll see an example in just a second. So a local linear approximation or a tangent line can be used in order to approximate values close to A. But where does it break down? Fairly quickly it starts breaking down, and it starts breaking down the big one, right? In the sense of values on a tangent line are going to be apart from values on the function itself. And what are we actually doing? If I was to go ahead and zoom in a little bit, aren't I using dy dx to approximate a value? And remember, dy dx stands for the slope of the tangent line itself. And why are we doing that? Because sometimes it's easier to plug into a linear equation than it is to plug into an actual function. The actual function, I have to actually change in x isn't a big deal, but change in y, plugging into the actual function itself can be a tough problem. So to get it exactly, I need to go ahead and go to a certain particular y value of my function. But if I use dy dx, basically, if I move somewhere on my tangent line, yay. But a linear approximation, to be honest, is one of the least useful approximations in the sense of it's only good for a very small interval. There are bigger approximations, so we have to wait until we talk about sequences and series. And our mind is going to be blown. This is actually the most basic approximation. It's just the only one that you've seen before. Let's keep going. Example. Find the tangent line approximation, or we could say the linearization of f of x equals 1 plus sine of x at, or we could say around, or centered around, or centered at the point 0, 1. Then use the table to compare the y values of the linear function with those of f of x in an open interval containing 0. You're like, let's just do the first one. Find the tangent line approximation. What do we do? Find the tangent line. How do we find the tangent line?
Derivative.
Derivative. That's one part.
And then y1, plugging the one slope.
Because remember, we're trying to y minus y1, stealing the y value, equals m. We'll get back to that. X minus x1. We go ahead and figure out the derivative. F prime of x is cosine of x. Plug it in. Nope, that's not a line anymore. I need to find the derivative. What did you say, George?
Or at 0.
At 0. George said it's okay. Cosine of 1 is, or cosine of 0 is 1. So I have y equals 1
Plus 1.
add the 1 over, plus x. Now looking really quickly at the page before. Is this the linearization? Yeah. How do we use the linearization?
You want to approximate where?
Or do they actually say where? No. So what are they trying to have us see? If we were to throw the following into a table, and as our y1, we would have our linearization, and as our y2, we would have our 1 plus sine of x. And if we were to go around 0, an open interval containing 0 meaning 0 needs to be in the midst, and we have some stuff on either side. Couldn't we plug in, for instance, like a -1/2 and a 1/2? Or a -1 and a 1? Gerardo, you were like, what's the big deal? Plug in. Can I plug in -1/2 to sine? No. Does that make sense? So I have no, with sine, I have to think about like pi over 6 and how that corresponds. That's almost 1/2ish, and I'd have to do a lot of mental work to even make an approximation. But here we could say, oh hey, what's 1 plus -1/2? 1/2. What's 1 plus 0? 1. What's 1 plus -1? 0. What's 1 plus 1/2? 3/2. What's 1 plus 1? 2. Now, remember, the further we get away from 0, the less precise our approximation is going to be, of course. But let's see how close we are on the approximations. Remember, all calculus based in radians, so we need to be in radian mode.
Is this a calculator type problem on AP or is it not even regular?
This wouldn't be on the AP. This is more of an exploration as to what's going on and how this is actually approximating that. So if I was to do 1 plus sine of what I have, -1, that would be 0.159. If I was to do, not super close, you're right, 0.5. Ideally, it's getting closer to 0 where it's centered around. It should be a closer approximation. This one is 0.5 to negative. 0.521. Ooh, not too shabby.
Pretty good.
Right? Not too shabby.
Oh, I keep thinking we're trying to get closer to 0.
Plug in 0. Well, that's the point of tangency. He's perfect, right? Plug in 3/2.
It's going to be,
Oh, sorry, 1/2, not 3/2.
0.5.
1.479. Not too shabby, right? Like, would we have guessed those right values for sine of x? Probably not. But just by plugging it into a quick tangent line, as long as it's close to the point of tangency that I know for sure, I'm good. I'm golden. I'm ready to go.
1/4.
And then sine of 1, 1.841.
1/20th.
1/20th.
No, that's close to 0.
Let's do a method next to So I'll go ahead and do it just so that you know. So 1/20th would be 1 plus 1/20th, and what would that be as a decimal? 1.05. Right?
0.05.
So 1.05, and then if you go ahead and do sine of 1/20, 1.04997. No, 998.
Wow, that is really close.
Isn't that cool?
This is
So what we couldn't do before, we can do with a tangent line. As long as you're close, it's a good approximation. If you're farther,
Not like
Do one.
0.00001.
it'd be a very stinking close approximation. Now,
I hate the approximation that's like
let's apply. What if I wanted to, now you're going to have to think a little deep on this, what if I wanted you to approximate the square root of 123, and I wanted you to approximate the cubed root of 26. Go! 11-ish and 3-ish. I want better. 11.1-ish because I'm guessing, and 2.9-ish because I'm guessing. No. Wait. What function is this?
root x.
What function is this?
Cube root x.
Where would I want to center a tangent line if I'm trying to get the best approximation that I can with what we know right now, which is just a linear approximation?
f prime of 1, 2, 3.
No, f prime of 11.
I am going to do f prime, but we need to go ahead and make a plan first.
F prime of 11.
Where are we trying to center this at? What is close to 123? 121. So I could do 11. Wait.
Oh, we could do 12. No, not 12.
Is 11 the x?
121 then.
121 is the x. Right? 11 is the y. Whew, that's close. But I do need to find my derivative. Do you guys see why? I need my slope.
1 over 2, 11.
F prime of 121 would equal
Over
1 over 2 square root of 121. Is that okay?
So
1 over 22.
So that'd be 1 over 22.
Yeah, please.
Right?
And that street and do some witchcraft.
So I could say y is equal to my linearization that I'm going to use, 11 plus 1 over 22 times x minus 121.
Now we plug in 123.
Now, for our linearization, if we want to use the same that they're doing, the reason why they don't like to use y and they're using L of x instead is so that we make sure that we keep everything separate in the sense that these aren't the y's of the original, right? They're approximates. So you could say, hey, we want to figure out the linearization of who or at where? Does that make sense? And I can say that that is 11 plus 1 over 22 times 123 minus 121, right?
Wait, what is that little angle looking thing?
L.
Oh, sorry, just L. I did the L of x, that's our notation for the linearization. So the y is not really the y of the original, that's why we call it L of 123. So the linearization of 123 from what I have is 11 plus 2 over 22 would be 1 over 11, right? And 1 over 11, isn't that?
21 over 11, so it'd be 120.
It would be 122 over 11.
Yeah, it
So
would be 122 over 11.
11.090909.
Yeah, if we actually went into decimal, it would be 0.09090.
Is this how they found like
So I could say
square
the
roots
square.
and stuff?
Maybe it's not a slide rule kind of It was how people, especially people in math, were able to do things like sine values, cosine values, log values, etc. without a calculator.
With calculus.
I think it's kind of based on calculus. Elijah gave me one. He gave me directions. I knew how to use it.
I couldn't figure it out.
It was fun.
He's a champ. Did you guys check it out? How close were we?
11.09053651.
No way! Really? Isn't that cool?
0.00.
How do they find the exact value of square root?
Plug it into a
We have to
calculator.
get more and more precise. And remember I said linearization, local linear approximation, is only one type of approximation. We can actually approximate with quadratics and with cubics and with quartics, but we have to learn about something first. How do we do the next one? Oh, for this, yes, go.
So we found the tangent line,
Stink.
and then why did we plug in L?
Because we're using the tangent line like we did in the last example at the beginning. It's centered at 121. We want it at 123. We don't know how to plug into the square root and solve with our mind, but we know how to plug into the line and get pretty close. Does that make sense? So here's the sad news.
Three, or not three.
We didn't do that one, and then we didn't talk about applications of differentials.
Oh, differentials are fun.
The differentials are easy because all you gotta do is just solve for the derivative and get dy alone, right?
Does that mean we're doing complicated integrals?
But then
in
we
this
might
chapter?
know we're not doing complicated, but we are going to anti-derivatives in chapter 6. But what we didn't get to do is practice with error. Kiddos, do the best you can on 5-5. But I think tomorrow we're not going to start with homework questions. We're going to skip that until Friday. We're just going to finish 5-5, go into 5-6, and then.
What was it called?
Sound good?
Appropriated error?
Yeah, propagated.
Oh, propagated.
All right, cool kids. I'll see you later.